So the next concept we're going to be looking at is the Laplace transformation. So Laplace transformation is a special transformation that converts a signal from the time domain, which is our normal operating domain, and then we convert that into the Laplace domain, which is also known as the frequency domain. So the preliminary is we need to ensure that the signal itself is kind of limited in energy. So we basically say that the integral f of t e to the minus sigma t, the absolute value of that should be less than infinity. So if that function satisfies, if a function f of t satisfies this equation, then we can say that the Laplace transformation exists. And then we say Laplace of f of t, which is given or symbolically written as the script L times of f of t, is defined equal to, so this term over here, is used for defined equal to. So that's defined equal to integral 0 to infinity. Here it's going to be little f of t times e to the minus st times dt. So here s is defined as the Laplace operator, and s is typically a complex number written as sigma plus j times omega. J is the imaginary number because we use current in electrical and control systems. We use the letter j, and then we typically never calculate this by hand. So we're going to look at some interesting or useful properties of the Laplace and kind of give a hint of where this came from or why this was important. So if you look at the Laplace of k times f of t, so essentially k is a scalar factor that is equal to k times f of s. So if you look at the sum or the difference, so the Laplace of f1 of t plus f2 of t would be equal to f1 of s plus f2 of s. If you look at the differentiation, the d over dt of f of t would be equal to s times f of s. So notice that it becomes multiplication by s, and then minus f of 0, little f of 0, which denotes the initial value of little f. So again, the little f's denote functions in the time domain, and then capital F denotes the function in the Laplace domain. And so we can extend this to like a higher order differentiation. So d to the n f little f of t divided by d t to the n is given by s to the n times capital F of s. So this is the only term that involves, so this first term is the only one that has capital F. So rest of it on following that are going to be the derivatives of little f of t. So we basically have s to the n f of s minus s to the n minus 1 f of 0. So this is the actual value at time equal to 0 minus s to the n minus 2 times f of 1. So this basically is df over dt. And so we keep going on and on. And so this is basically f to the n. So this is basically short form for writing d to the n minus 1 f divided by dt to the n. And so we keep going, and we can kind of write the derivative like that. So we can similarly do the integral. So the integral from 0 to t f of tau d tau. So the reason we use tau here is because we want to differentiate, the t appears in the integral, so we want to differentiate the letters. So we write it as f of tau d tau. So this becomes 1 over s f of s. So the point to note here is that the Laplace transformation has the advantage of converting derivative or differentiation due to multiplication by s, and similarly if you have the integration, so that becomes a division by s. So this is fairly powerful, particularly when before the time when you actually had like computers to do numerical simulations, you could have still done the calculation, and this is where we have a lot of the theories regarding the stability and all of the analysis of our system is based on this Laplace transformation over here. So the next important property is the time shift. So if you look at this function over here, so the Laplace or f of t minus capital T times u of t minus capital T. So what we're essentially saying is we are looking at the signal starting at time capital T. So if we look at that, so what is u sub s? So that's actually a unit step. So if you wanted to plot the step and then you have the time here, so this is how this step actually looks. So if you look at the Laplace of the time shift, so that is given by e to the minus capital T times s times f of s. The other two properties that we have is the initial and the final value theorem. Initial value of little f of t is given by limit t going to 0 of f of t. So that's given by limit s tending to infinity, s times f of s. And then similarly, we have a final value theorem, which is the value of f of t as t goes to infinity. So that's given by limit s tending to 0, s times f of s. So here's a simple example. So we would like to calculate the initial and then final value of 1 plus 1 over s plus 1. So you can pause this video and then upload the results. So the initial value is given by, going from the previous slide, is given by limit s tending to infinity, s times f of s. So we substitute that value, so it becomes limit s tending to infinity, s over s plus 1. So the problem here is if we substitute infinity and infinity, so we'd actually have infinity over infinity, which is not defined. So we need to do something different. So what we do is multiply and divide, or rather divide the numerator and the denominator by s. So that gives us 1 over 1 plus 1 over s. And then if you can take the limit as s tending to infinity, this term over here becomes 0. So this becomes 1 over 1. And so our initial value is 1. Similarly, if you wanted to calculate the final value, so that becomes limit s tending to 0, s times f of s. So here it becomes s tending to 0, s over s plus 1. So we don't want to do the same trick over here because 1 over s would give a, we can directly substitute for 0 and there shouldn't be any issues. So if we do that, we get 0 by 0 plus 1, which basically becomes 0. So now we're going to look at some of the applications of the Laplace transformation. So recall the spring mass damper equation that we had, which was m y double dot plus b y dot plus k y is equal to little f of s, so f of t. So what I've actually done is replaced the input u with f. So we're also given that the y at time equal to 0 and then y dot at time equal to 0 is 0. So we will define the Laplace of these variables. Particularly, we start with the Laplace of y. So we'll define capital Y of s as the Laplace of y of t. Similarly, we'll define f of s as the Laplace of little f. So when you do that, then we need to next calculate the Laplace of y dot and y double dot. So the Laplace of y dot, if you recall, is s times y minus y of 0. Because y of 0 is 0, this basically just gives us s of y, s of capital Y, s times capital Y, excuse me. And if you do Laplace of y double dot, this becomes s squared capital Y minus s y of 0, little y of 0, minus s to the 0, y dot of 0. So s to the, so all of these values, little y of 0 and y dot of 0 is 0. So that basically means Laplace of y double dot just becomes s squared times y. So the other property that we use is because the sum of the Laplace is equal to the Laplace of the sum. So we can basically just substitute, simply substitute for y dot. If you're basically doing the Laplace of this whole equation, we can just take the Laplace of the individual terms and then add them up. So that basically means we get m, and then we substitute for y double dot, the Laplace of y double dot. This becomes s squared times y plus b s times capital Y plus k times y. And then we can just rearrange the terms and we basically get capital Y, so divided by f. So we just take all of these terms is 1 divided by m s squared plus bs plus k. This is called the transfer function and is typically denoted by the letter G. All right. So next, we're going to look at basic usage in MATLAB. So we're going to create an impulse response, a step response, Bode plot, and Nyquist plot of the transfer function 16 divided by s squared plus 10s plus 16. So again, if you're doing it manually, it's a lot more work. We're going to use the power of MATLAB here. So the function that we're going to use is known as TF, or transfer function, to actually create this transfer function. So I've already opened MATLAB over here. So if you wanted to figure out what things are, so we're going to go and then type help and then TF, and then it tells you all of the help that is available for this particular function. In particular, how is it that you're going to create this function, and then how would you use it, and so on. And it also gives an example. So if we scroll up over here, so it says one of the ways you would create it is you have TF and then you have numerator, comma, denominator. You can also create it, give sampling time, you're creating a discrete time, so it's a signal, we're going to ignore it. We can also create it, create S is TF of S, and then do it in different ways. So we're going to look at doing something, creating a numerator and denominator polynomial. So the way numerator and denominator polynomial are going to be is that they're going to be in decreasing powers of S. So let's create that first. So we'll create the numerator and denominator, and then use that to create our polynomial. So the first thing we're going to do is we're going to store the different powers of the numerator and the denominator in two separate variables. So in MATLAB prompt, we're going to say numerator is 16 and denominator is it's 1 times s to the 2. So we're going to put 1, and then 10 times s to the 1, and then 16 times s. So these are the values we're going to be storing. Again, so these are going to be the, so we just grab the coefficients from each power of s and then put it in here. So let's do that in MATLAB. So CLC, so we go numerator, (16). So notice that it prints the stuff on the screen, which I don't like too much. So what I'm going to do is make it without printing. So we're going to go add the semicolon. So this becomes denominator is 1, 10, 16. So now it doesn't print anything. And then what I'm going to do is create a transfer function. We'll call that G. So this is going to be G is TF of numerator, comma, denominator. So this creates our transfer function. So then we go back and see if we can do all of these plots. So or rather next, we are going to create, use transfer function to create the transfer function. So next we just use impulse of G, step of G, Bode of G, and anything else that you want, and then create those corresponding plots. So let's do that. So we're going to go impulse of G. So this is the impulse response. So here we have the impulse response, we have the time, and then the amplitude. So the impulse response is kind of like giving a kick to the system. So we can next do the step response of the system. So instead of impulse, we try the step, and then we hit enter, and then we're going to get the step response. So that's the figure over here. And we can similarly do the Bode plot of the system. And so we do the Bode plot. So this gives the frequency here, and then this is the Bode magnitude and the Bode phase over here. And similarly, we can also do the Nyquist of that particular system. And so we do the Nyquist, and then it plots it in the same figure. And so this is the Nyquist plot. So this is the stability point for the Nyquist, and then this gives the Nyquist plots itself. So just this once, I'm going to also show you an equivalent software, which is an open source software called Octave. So we're going to pull that up over here. So you can download it. If you just search for Octave, it'll tell you how to get the software. And so what we're going to do is I've copied the steps already, so I'm going to just do the impulse alone. So I'm going to copy and then paste this here, and then it opens up a figure, and then notice that the impulse response is fairly similar. Let's do the Nyquist and then see how it looks. And so this is the Nyquist plot. So this looks fairly, so it's doing the same calculation, so it should look fairly similar as well. So again, so this is an open source software. It's called Octave. It usually has most of the functionality of MATLAB, but it lacks some of the advanced functionality. So this is actually useful if you don't have an access to MATLAB, and then you can kind of do most of the calculations in Octave as well.